Hello everyone, thanks for joining me. Today we're going to talk about a painful truth that cuts across many areas of pure mathematics. We're going to talk about the so-called fundamental theorem of algebra, which is a mainstay not just of algebra but many adjacent areas of mathematics. And we're going to call it into question today, into serious question. And we're going to see that the implications in adjacent fields are very considerable. Now, what is the fundamental theorem of algebra? Well, it's the statement that a polynomial equation setting equal to 0 always has a solution over the complex numbers. Now, some of you may not be that familiar with complex numbers, so there are alternate formulations of it, or pretty well close to being alternate. And another one to maybe think about is that if you have a polynomial, for example, the polynomial f of x equals 2 plus x to the 5. Okay, 2 plus x to the 5. That's a polynomial function. You input an x, you calculate 2 plus x to the 5, and you get a number. And so one statement is that there is a complex number, something of the form a plus bi, that when you plug that in there, you're going to get exactly 0. That's sort of the standard statement of the fundamental theorem of algebra. Another statement is that this particular polynomial factors into linear and quadratic factors. That has a pleasant aspect in that you don't really need to know anything about complex numbers. It's purely a statement over the rational numbers or the real numbers, so it's just restricting ourselves to the usual one-dimensional number line. Okay, so what's my position on this? Well, before we talk about that, let's just talk a little bit about the history of this thing. This is a very illustrious result with a long history going back at least to Euler, who worked on it a little bit, wasn't able to understand it completely. And then usually the first clear proofs are attributed to Carl Friedrich Gauss, the preeminent German mathematician of the early part of the 19th century. Gauss, through his career, came back repeatedly to this particular topic and gave a number of different proofs. In retrospect, those proofs are perhaps of a topological nature. Okay? They rely on concepts which really hadn't been developed systematically at that time. And probably Gauss knew this at some level and was a little bit unsatisfied with his earlier proofs. So he kept on coming back and trying to find like a better argument. And actually, since Gauss's time, many people have come up with alternate proofs of this fact. In my view, none of them are correct, for the simple reason that the theorem itself is not correct. The fundamental theorem of algebra is in fact not correct. Okay, so let me try to explain that. Okay, and this is a kind of a remarkable statement because it's directly in opposition to what pretty well every pure mathematician on the planet believes fervently, okay? But it's a situation where the evidence is pretty clearly on my side. So from my point of view, it's some kind of remarkable sociological aspect of the mathematical world that somehow we are able to uniformly ignore all the evidence that points to the fact that this is not a completely correct theorem. So what am I talking about? Well, let's go back to that example that I started with. F of x was 1 plus x to the 5. Was that? Let's say that's the polynomial I referred to. 1 plus x to the 5. So the question is there a complex number x of the form a plus bi that you can plug in to that to get 0? And I say that there isn't. There just isn't. Now, my fellow colleagues will say, well, yeah, yes, there is. And I'll say, no, there isn't. And they'll say, yes, there is. And I'll say, no, there isn't. And if you're listening from externally, you hear a lot of yes, there is, and a lot of me repeating, no, there isn't. But at some point, you're going to say, well, wait a minute, guys. Why don't we decide this scientifically? It's not a question of a majority opinion, it's a question of who is actually right. Okay, so Wildberger is asserting that there is not such a thing, and you guys are asserting that there is such a thing. So the onus seems to be on you to demonstrate that there is such a thing. Okay, so please exhibit the number a plus bi, such that when you plug this a plus bi into f of x equals 1 plus x to the 5, that you get 0. And at that point, the room will empty. Oh, they all have something else that they suddenly need to do. And we're here just all by ourselves. Okay, what happened? They all know that they can't do this. They can do it approximately. Oh yes, and that's in itself a very powerful statement. Okay, so it's undoubtedly true, and well, not undoubtedly true, it's almost surely true, okay, that you can find complex numbers of the form a plus bi, that when you plug into f of x, you're going to get some number, some complex number, which is approximately 0. What does that mean? Well, that means that its size is approximately 0. Well, what does that mean? Well, the best way of thinking about the size of a complex number a plus bi is to think in terms of the quadrants, which is a squared plus b squared. So a squared plus b squared is a measure of how big that complex number is, or how far away it is from 0. And what we're saying is that if we want that quadrants to be small, say less than 1/1,000th, then we can actually find a complex number a plus bi for which that will be the case, that f of x actually has quadrants less than 1/1,000,000th. That in itself is quite a remarkable statement, but that is not the current statement of the fundamental theorem, okay? The statement is rather that there is a number that you can put in there that you get exactly 0. So if I ask my computer, any of the powerful mathematical softwares that are around there, to come up with such a complex number, they'll all be able to come up with approximate zeros in this sense. They'll be able to give you decimal expansions of the a and the b, which have this approximate property. They're approximately 0 when you feed them into this function. But none of them are able to come up with an a plus bi, which exactly gives you 0. And of course, the reason is that to get such an a plus bi actually requires an infinite amount of work. So what you can do is you can sort of create a sequence of numbers, so one step at a time, always getting a little bit closer to 0 in terms of the final result. Okay, so there's your first guess. So now we adjust that to get something a bit closer to 0, and then we adjust that to get closer to 0. So we can keep on getting closer and closer to 0. But this is an unending process that never ends with going with the step, oh, now we're exactly at 0. That doesn't happen. You're always just getting closer, but never actually getting to the end of the rainbow, right? So the way modern pure mathematics gets around this is by somehow pretending that this sequence, this unending sequence, which never gets there, somehow gets there in the limit. So then there are these religious invocations that are brought forward. That, yes, well, but in the limit, in some other alternate universe, we can create some infinite decimal a plus bi, which actually does work. We can't exhibit it in this universe, but in our thoughts, in our minds, in this alternate universe, which has an infinite amount of memory, we could create such a thing, assuming we were allowed infinite memory and infinite power and infinite, computational resources. You see the problem? Right, if we want to restrict to the reality of the world in which we live in, the fundamental theorem of algebra is wrong. And the different manifestations of it are also wrong. So the manifestation that you can factor a polynomial into linear and quadratic factors is also wrong. So let's talk about this manifestation of the theorem, which allows me to say some very important general facts about the mathematical world. Okay, when we're first learning arithmetic, we learn arithmetic with natural numbers and then integers and then maybe fractions. So we're sort of enlarging our domain of arithmetic, still staying in the general ballpark of numbers. We recognize these are all different kinds of numbers, and we're sort of extending our arithmetic to these larger and larger classes of numbers. Fine. Then at some point, we make the shift to algebra, where we introduce things which are a little bit different from numbers. They're more complicated than numbers, called polynomials. Okay? And these polynomials also have a kind of an arithmetic, but we call that arithmetic algebra. So we still add them, multiply them. Sometimes we can divide them. And this algebra is very useful in practical applications and connects in a lovely way with geometry and combinatorics and analysis. And it's really a kind of a powerhouse of modern mathematics. But algebra, in some sense, it's a kind of a glorified arithmetic where we've extended the domain of consideration from numbers, like natural numbers, to these more general things called polynomials. I like to call them polynumbers, because I like to think of them just in terms of the lists of the coefficients. To me, that's the essence of a polynomial. Okay, in the world of numbers, like natural numbers, the fundamental theorem of arithmetic, which is that a natural number can be written as a product of prime numbers in an essentially unique way. That's a fundamental fact. Okay, so that any number that you get, even if it's really big, you can write it as a product of primes, at least, if the computational resources are sufficient to deal with the size of that number. Over in the polynomial world, factorizing and factorizability is also an important aspect of the story. And arguably, it's actually more important. So when we start doing algebra and higher dimensional algebra, linear algebra, geometry, etc., the issue of the factorizability of polynomials, and polynomials not just in one variable, but in more than one variables, like involving x's and y's, or x, y's, and z, etc., that becomes a really important issue. And if you do a lot of research, in the intersection of geometry and algebra, you will gain a great appreciation for the wonderful software resources that have been developed in the last few decades that enable efficient polynomial factorization. These are sort of unsung heroes of modern mathematics, these algorithms which underlie the computational power of our computers mathematically. So if you have some big polynomial, perhaps in several variables, that arises in some situation, almost invariably, your first question is, or ought to be, does this thing factor? And our computers are really good at finding factorizations of polynomials. It's a beautiful and so helpful and powerful thing. Okay? So I want to impress upon you that our computers are really good at factorizing. So, for example, if you take a cubic polynomial and another cubic and a quadratic and a 5-degree polynomial and a couple of linear polynomials, and you multiply them all out, okay, you give this to some person and say, can you factor this? It'll take them a long time to factor it. But our computers can do it almost instantaneously. And it's a remarkable and beautiful thing. And if you have a polynomial that arises in a situation and it factors, it almost invariably says something important about the underlying situation that you're investigating. So it's not just a pleasant aesthetic thing. It actually has deep consequences in terms of the structure of the mathematics that's involved. Okay, so I'm impressing upon you that this factorizing issue in polynomials is actually practically more important in the algebraic or polynomial context than it is in the arithmetical or number theoretical context. Okay. So having said that, it's a crucial issue whether some given polynomial, say just in one variable, actually does factor or not, and how it factors. And here, my friends, is the reality. Okay. The reality is that most polynomials, in some sense, don't factor. And if they do factor, typically they only factor partially. So if you write down a polynomial of degree 23, okay, and you choose the coefficients to be integers, sort of randomly between 0 and 100, okay, there's almost no chance that that big polynomial that you get will factor. Especially, there's no chance that it's going to factor into linear and quadratic factors. Almost no chance. Okay, of course there's a chance, but it's very unlikely. The fundamental theorem of algebra asserts that, no, Norman, it always factors into linear and quadratic factors. But that is just demonstrably not true. So you just pick a polynomial, you make up a polynomial at random, and you go to Mathematica or Maple or any one of these mathematical software packages, and you ask it to factor this thing, and it will not be able to factor it unless you've sort of cooked it up in the right way beforehand, namely by doing what I said before. You start with some small polynomials and multiply them together, and then naturally the result is going to be something that factors. And you see, and here's where a certain amount of subterfuge is involved in modern mathematics education. So in applications of this result, so one important application is to the integration of rational functions. So my mathematical peers believe that rational functions, like polynomials divided by polynomials, are all integral. There are closed formulas for the integrals of these things. That is not true. It's just not true, people, okay? And the usual thinking all rests on this fundamental theorem that you could take the denominator and factor it into linear and quadratic factors. Then you can perform some pleasant little algorithm called partial fraction decompositions. Then you get these sort of individual things that all have denominators which are either linear powers of linear factors or powers of quadratic factors. And then you have particular formulas to deal with those two special cases. And that argument supposedly suffices to integrate a rational function in general. But ladies and gentlemen, it's just not true. It's just not the way the mathematical world is. It's much more subtle and complicated than that, okay? The reality is that if you have a polynomial and it has, in the denominator, there's a 5-degree thing and a 3-degree thing and a 7-degree thing, okay? You can do partial fractions, but you're not going to get around the fact that you've got a 5-degree, a 3-degree, and a 7-degree thing there. You cannot actually find linear and quadratic factorizations of those things in general. So that consequence that we can integrate rational functions is simply a wrong conclusion, and it's a misunderstanding carried by essentially the entire mathematical community. Let me give you another example to do with linear algebra. So if you have a symmetric matrix, okay, in linear algebra we like to do something called diagonalization. And there's this standard theorem that says that symmetric matrices are diagonalizable. Okay, you multiply by something on the left and right, and then what you end up getting has a very nice form with mostly zeros, just non-zero stuff along the diagonal. Okay, so this has a lot of practical implications, very important in applications. However, it's not really true. And it's not true because the essential computational result is finding the eigenvalues and eigenvectors. And it's the eigenvalues that are the problem. Because to solve the eigenvalues, you have to solve the characteristic polynomial of this matrix. And that, in general, does not have zeros. In opposition to what the fundamental theorem tells you. The fundamental theorem says, well, we're working over the complex numbers or whatever, it always has linear factors, it always has zeros. But in fact, in practice, it doesn't. That's just not true. So again, in linear algebra courses, you are presented with all these examples, carefully constructed examples that make it look like the algorithm that you're presented with works rather generally. But they've all been cooked up carefully to ensure that the characteristic polynomials that end up being involved all have nice linear and quadratic factors because they're built in to begin with. They're not random polynomials. So there's much more to be said in this direction, and there are lots of other applications, okay? But these are two really good applications. So in general, the integration of rational functions is not in general possible. And furthermore, the diagonalization of a general symmetric matrix is not in general possible, although both of these things can be done approximately. That's true, but not exactly. And it all stems from this fundamental confusion about the fundamental theorem of algebra. So what's the solution? Well, the solution is to acknowledge the way the mathematical world is, not fight it, not try to stomp your feet and make it something that it's not, and think that you can do that by some appropriate axiomatic sleight of hand. You can't. You can't change the way mathematics is. But you can acknowledge what's really the case. Now there is, as I mentioned before, there is a result in this direction, almost surely. But I say almost surely because we don't really know, because we don't have a proper enunciation of this fact and we don't have a proof. So the theorem, or one of the versions of the theorem is the following, that if you have a polynomial, okay, and you have a quadrant specified, maybe 1 over n, n is a big natural number, that you can find a complex number. When you plug it in to the polynomial, you're going to get a result whose quadrant is less than the given 1 over n that you've chosen. So you can make the function's values arbitrarily small, okay, arbitrarily close to 0. And that's already a very powerful statement and is sufficient in applied mathematics to, approximately deal with these various applications that I've talked about. So you can still approximately integrate rational functions. You can still approximately diagonalize symmetric matrices, and that's, what applied mathematicians need. They take care of the approximations. They take care of errors. They're careful about these things, okay? But there is a result in this direction, and people should know that this result has not yet been established. So this is a result that can be stated purely in terms of rational numbers. You do not need any real numbers for this, right? You've got a polynomial with rational coefficients. We're asserting that there is a complex number of the form a plus bi, where a and b are rational numbers. So when you plug it in, okay, you're going to get a complex number whose quadrant is less than 1 over n. You've chosen n before n. Maybe n is a million. Okay, no matter what n is, you can find a complex number a plus bi that when you plug it in, you're going to get a number whose quadrant is less than 1 over n. That is an incredible statement. That is, in my view, close to being the real fact of the matter. But crucially, that is not a result which is a theorem of modern mathematics. That is a result of future mathematics. I don't believe that any of the proofs of the fundamental theorem actually are careful and precise enough to establish that result, which is purely in the context of rational numbers. So this is a major to-do. In my view, if you want to become really famous, okay, figure out how to prove this statement. Preferably in a computationally explicit way. So give a procedure, an effective procedure that guarantees, that explains how you get that a plus bi given the 1 over n limit on the quadrants that we want. Hugely important. Absolutely hugely important. Okay? In my view, if you prove that, that's better than any theorem proven in the 20th century in analysis. That's my view. Okay, so that's an unsettling kind of talk, and I know people will strongly kick and scream. And the implications of this go much further than what I've just said. So this understanding that I'm sharing with you today actually, to be honest, also is like a dagger into the heart of one of mathematics' most illustrious and distinguished fields, which is algebraic geometry. So we're going to have to talk about that. I'm Wildberger. Thanks for listening.